All right, hi everyone. Welcome back to the section 6.3 video. And in this video, we're going to solve another differential equation using the method of Frobenius. But for this example, we're going to use the initial equation first to verify that our initial roots are the same and that we're doing the problem correctly, okay? So we're just going to know them beforehand and use it as a good check. So here we have the differential equation, 2xy double prime plus 1 plus xy prime plus y equals 0. We want to find the solution to this about the regular singular point x equals 0. And remember, that's just a power series of the form n equals 0, a sub n x to the n plus r. Okay, but first we want to use the initial equation to have our roots beforehand. Okay, so let's come over here. Let's start our solution. All right, so solution. First thing we're going to do is use the initial equation to know roots, which are, R1, R2, so R ahead of time. Okay, so remember that initial equation, it's going to be, R times R minus 1 plus A naught R plus B naught equals 0, and we solve for R. Okay, and these roots relate to our series solution because remember our final solution is going to be something like x to the r times a power series a n x to the n. Okay, so we're trying to figure out what this x to the r is. We're going to get two of them. One might be r equals 0, but we'll see when we do the problem. Okay, so we have a couple of things we need to figure out. We need to figure out a naught and b naught. We need to figure out what those two constants are. And so the way to do that is take our differential equation, 2xy double prime plus 1 plus xy prime plus y equals 0. And what we want to do is get this differential equation into standard form. Okay, meaning we want to get that y double prime naked because standard form is y double prime plus p of x y prime plus q of x y equals 0 so that we can figure out what p of x and q of x are. That helps us figure out what a naught and b naught are. Okay, so get this into standard form. We're going to divide by 2x all across. And so what we get is y double prime plus 1 plus x over 2x. All right. Y prime plus 1 over 2x, y equals 0. Okay, so that means p of x is this 1 plus x over 2x. And q of x is this 1 over 2x. Okay, and so we still need to figure out what a naught and b naught are. We're still on that path to get that. So before we do, we need to figure out little p of x and little q of x. So little p of x is just x times capital P of x, which is x times 1 plus x over 2x. All right. We multiply x times this, the x's cancel out in the numerator and denominator. So what I get is 1 plus x over 2. Okay, so that's little p of x. And now little q of x is x squared times capital Q of x Okay, and that's x squared times 1 over 2x. The squared and the x cancel out, so what I'm left with is just x over 2. Okay, so that's my little pvx, that's my little qvx. And so when we're trying to find a naught and b naught, a naught is little p evaluated at 0. So I'm going to take that 1 plus x over 2 and evaluate it at x equals 0. And so what do I end up with? I end up with just 1/2 when I plug in 0. Okay, so that's A naught. And now B naught is Q, little q evaluated at 0. So that's just x over 2 evaluated at x equals 0. So I'm just going to plug in 0. That would be 0 divided by 2, which is just 0. Okay, so that is B naught. Okay, so I have A naught, I have B naught. I can use my indicial equation and figure out what my roots are going to be. So the indicial equation is going to be r times r minus 1 plus A naught, which is 1/2 r, plus B naught, which is just 0, equals 0. So now let's just go ahead and solve for r. So, distributing the r's becomes r squared minus r plus 1/2 r equals 0. Combine the negative r plus the 1/2 r. This becomes r squared minus 1/2 r equals 0. Factor out an r. This becomes r times r minus 1/2 equals 0. And so if I solve for r, this would be r equals 0 and r equals 1/2. Oops. And these are our initial roots, which come in handy later on. Okay, so within the solution process, we're going to be able to find what um, our roots are without having to do this initial equation, but doing this is a good check to make sure that we're doing the problem correctly, okay? Because if you're not doing the problem correctly, you won't get these roots, okay? So it's a good check. So we'll keep this in the back pocket, and now let's just go ahead and try and solve our differential equation. So now, back to solving the differential equation, using the method of Frobenius, we try to find a solution of the form, okay, like we talked about previously, a solution of the form y equals index starting at n equals 0, a sub n, x to the n plus r. Okay, so just remember, this is a solution about the regular singular point x equals 0. Okay, think about it as like x minus 0 to the n plus r. So we're trying to find a solution of this form, and we're going to need to plug this into the differential equation from up above. Okay, so that means we're going to need a derivative. We're going to need a second derivative. So let's go ahead and get those. So y single prime. Remember, for Frobenius method, and when we have this exponent r, when we take the derivative, the index doesn't change. It still stays at n equals 0. So the first derivative would be n plus r, a sub n, x to the n plus r minus 1. Okay. And y double prime is going to equal, starting out at n equals 0, n plus r times n plus r minus 1, a sub n, x to the n plus r now minus 2. Okay, so those are our y prime, and y double prime. Now what we're going to do is plug them into the differential equation. So plugging into the dE, okay, our differential equation is 2x y double prime plus 1 plus x y prime plus y equals 0. So plugging in our y prime, y double prime, what I get is 2x times the power series, starting out at n equals 0, n plus r, n plus r minus 1, a sub n, x to the n plus r minus 2, plus 1 plus x times the power series y prime, which is going to be n equals 0, n plus r, a sub n, x to the n plus r minus 1, and then plus y, which is just going to stay itself. Power series starting out at n equals 0, a sub n, x to the n plus r, and it's all equals 0. Okay, so this is our start, and now we need to clean it up a bit. We need to distribute in this 2x. Yeah, it's gonna get rid of this negative 2 here. We're going to distribute in this 1 plus x. So we're going to pick up 2 terms here. And that x would cancel out the negative 1 there. Let me erase that. But yeah, so we're going to pick up 2 terms because 1 is going to multiply the power series and x is going to multiply the power series. So what comes out of this is the power series, n equals 0, 2 times n plus r minus 1, a sub n, x to the n plus r. Minus 1. Okay, because that power of x is just like a plus 1 here. So it makes it just minus 1 now. Okay, so now we're going to distribute that 1 plus x to that power series. So we're going to get 2 terms out of that. So 1 times the power series is just going to be itself. So this will be power series n equals 0. N plus r is going to be the same exact thing. Okay, unchanged. But when I distribute in that x, what I'm going to pick up is n plus r, a sub n, x to the n plus r by without the minus 1, because if I distribute that power of 1, it'll be like negative 1 plus 1, which makes it 0. So I'm just left with n plus r now. Okay, and then this is unchanged, our last term, a sub n, x to the n plus r, and this all just equals 0. Okay, so now I have 4 terms now. So this 3-term series has turned into 4 terms. But the good thing about it is we can start combining some things. So notice here that my first 2 terms are x to the n plus r minus 1, both starting out at n equals 0. So what I can do with these two series is combine them. Okay. And likewise with my third and fourth terms, they're both starting out at n equals 0. They're both x to the n plus r. And I can also go ahead and combine them. Okay, that works out well because now I'm just going to be left with two power series. Quite long power series, but still two nonetheless. So what I'm left with, we could write it, is a power series starting out at n equals 0. It's, we put some brackets here just to maybe look like it's closing off a bit to show the difference of it between our second term, but brackets, 2 times n plus r, n plus r minus 1, a sub n x to the n plus r minus 1. And then we're adding that second term, right? So it'll be like plus n plus r, a sub n x to the n plus r minus 1. I'm going to close that off. Okay, and then my second term is going to be n plus r, a sub n x to the n plus r plus a sub n x to the n plus r, and this all equals 0. Okay, so for both of these, I think I want to factor out some common terms. Like in this first series, they both have a n x to the n plus r minus 1. So I'm going to factor that out. So what this will look like is a series n equals 0, brackets, 2 times n plus r minus 1. And I'm going to factor out the a and to the x plus r minus 1. So I'm left with just n plus r here, brackets, and I factored this out. an times x to the n plus r minus 1. Okay, and I'm going to do the same thing for my second term. They're both an to the x n plus r, so I'm going to factor that out. So this would be n plus r plus 1, and I factored out at an x to the n plus r, this equals 0. Okay, so I was trying to zoom in a bit, but it's getting a little glitchy. Um, what did I do here? I'll just say like factored out an x to the n plus r minus 1. And then here factored out an x to the n plus r. So that's what I did for both of these. Okay. So what can I do now? Well, let's look at this first term here. Um, this first term, 2 times n plus n plus r minus 1 plus n plus r. That's a little messy, a little repetitive. So we want to kind of clean that up a bit. So I'm going to just clean this up down below. So what do they have in common? They have n plus r in common, these two expressions. So I'm going to factor out an n plus r from those. So what this would look like is n plus r times 2 times n plus r minus 1 plus 1. All right, I factored out that n plus r. So, you want to simplify this. So I'm distributing the 2 here. So it'll be n plus r times 2n plus 2r minus 2 plus 1. And so negative 2 plus 1 just be negative 1. So what I'm left with is n plus r times 2n plus 2r minus 1. It's a lot cleaner, a lot less terms. If you left it like that, I mean, it'd be fine. It would just be a bit repetitive and, a lot less clean to work with. But, we simplified it, so that's good. So let's kind of come back to the problem now. And what we're going to do next is factor out some more terms. But let's just rewrite it. All right, just to have our next step. Okay. A sub n, x to the n plus r minus 1. Okay. Plus n equals 0. We could even just drop that parentheses. So it'll just be n plus r plus 1. A sub n, x to the n plus r. This all equals 0. Okay, great. So, remember what we want to do is get a solution, right? But we also want to get a solution where it's like x to the r times a power series. All right, so what I want to do here is factor out an x to the r. Okay, so I want to factor out an x to the r. I'm going to be factoring out, you know, this x to the r right here. Okay, they both have x to the r. Let's go ahead and factor that out. So this would be x to the r times the entire expression, n equals 0, n plus r, 2n plus 2r minus 1, a sub n, x to the n minus 1, plus n plus r plus 1, a sub n, x to the n, and this all equals 0. Okay, so last thing we want to do is combine these two power series. We want to get into one power series so then we can set up our recurrence relation and find out our solution. So we want to combine these. The issue here is that this first term is x to the n minus 1. The second term is x to the n. We want to get them both x to the n. So there's a couple things we're going to do here. Um, First, in this first series, we're going to peel off when n equals 0. Just this first power series, we're going to peel off n equals 0. So what that looks like is x to the r times, by plugging n equals 0 there, I end up with just r times 2r minus 1, a sub 0, x to the negative 1. Okay, so that's if I'm plugging in 0 here, 0 here, 0 here, and 0 here. All right, that's what I end up with. Okay, so this is when n equals 0. So that means my index now is going to start out at n equals 1. Okay, so let me rewrite everything. Our second power series is unchanged. Okay, all equals 0. Let me fix that. Equals 0. Okay, so this one n equals 0. And the reason we do that is because we want to index shift this power series, okay? So for here, we're going to index shift, okay? Because we want to get n equals 0, and we want to get x to the n. So if I index shift here, I'm going to get n equals 0, and I'm just going to get x to the n. That way I can combine these two series and make them one. Okay, so let's go ahead and try that out. So what this becomes is x to the r times r to r minus 1, a naught x to negative 1. Okay, times plus the power series. I'm now starting out at n equals 0. Since I'm subtracting 1, that means I need to add 1 to every single n in my power series. So this would be like n plus 1 plus r times 2, n plus 1 plus 2r minus 1, a sub n plus 1, x to the n plus 1 minus 1. And then this last series is unchanged. Okay. And so let's go ahead and simplify this middle term. This will be x to the r. This is unchanged. I'm just copying it down. And let's clean up this power series here. I'm going to rewrite it like n plus r plus 1, just to have the n and the r close together. If I distribute in this 2, right, and 2 minus 1 is 1. So what I end up with is 2n plus 2r, oops, wrong color. 2n plus 2r plus 1, a sub n plus 1, x to the n, because 1 minus 1 cancels out. So now I just have x to the n plus our unchanged power series. Okay, great. So we are almost there. Notice how our two power series both are x to the n and start out at n equals 0. So what we could do now is combine these two power series, and we're going to take an extra step. We're going to factor out an x to the n. Just do it all in one. So what this looks like is x to the r times 2r minus 1, a naught x to the negative 1 plus going to be one power series now, n equals 0, n plus r plus 1, 2n plus 2r plus 1, a sub n plus 1, plus n plus r plus 1 times a sub n, and I'm factoring out an x to the n. Okay, and just don't forget that equals 0, and it's all bracketed by x to the r. Okay, so we've all combined these to one power series. And all this means now is that, you know, this implies that that first term, when n equals 0, that r times 2r minus 1, a naught, well, that equals 0. And all these other coefficients equal 0 as well. So kind of a lengthy one. Let's go ahead and write it that n plus r plus 1 times 2n plus 2r plus 1 a sub n plus 1 plus n plus r plus 1 a sub n all equals 0. Okay, so for our first equation, um, you know, we can note that nothing is gained from a naught being 0. That will just ruin our whole solution. So in that case, we must have that r times 2r minus 1 equals 0. So we solve for r. That means r equals 0, 2r minus 1 equals 0. So r equals 0, and r equals 1/2. And so these are our indicial roots. Okay, these are our indicial roots. They're going to be our two solutions for this differential equation. And at the beginning of the problem, we found them. And they're the same exact ones, r equals 0, r equals 1/2. So it actually checks out. Checks from indicial equation. Great, that means we're on the right track. Everything looks good. We're on no mistakes so far. So it's a good check, okay? So got our roots. We know what our two solutions would look like, what those roots would be. And now it's time for like the recurrence relation. Okay, so we're going to use this very long term here and set up a recurrence relation. So remember, we always want to solve for the higher an. So we're going to solve for an plus 1. So I'm just going to move everything over to the right-hand side. And so if I do, what I'm left with is negative n plus r plus 1 an, all divided by n plus r plus 1, 2n plus 2r plus 1, a sub n plus 1. Oh, excuse me. We already solved for that. I'm just copying it down. Okay, so what cancels out here? The n plus r plus 1. That's great. So my recurrence relation is an plus 1 equals negative an all over 2n plus 2r plus 1. And this is for n equals 0, 1, 2, etc. All right, this is my recurrence relation. And why am I starting out at n equals 0? Well, that's just where my power series is starting out. Okay, so that's my recurrence relation. But now we need to find the power series solutions for both of these roots, r equals 0 and r equals 1/2. So what we need to do now is substitute R1 equals 1/2 and R equals 0 into the recurrence relation to get two different recurrence relations and giving us two different solutions. Okay, so if I plug in R1 equals 1/2 into this recurrence relation, so I'm plugging in, 1/2 right here, what will I get? So let's see. So for R1 equals 1/2, what I get is an plus 1 equals negative an all over 2n plus 2 for n equals 0, 1, 2, etc. Okay, now for r equal 0, if I plug 0 into my recurrence relation, I get negative an over 2n plus 1. Okay, and that's for n equals 0, 1, 2, etc. Okay, great. So let's set up these recurrence relations, and then let's get two solutions to these. So let's set up the first one. For, here I'll say like, 1 and 2. So for 1, for R1 equals 1/2, the recurrence relation is an plus 1 equals negative an over 2n plus 2. Let's go ahead and start plugging in n. So for n equals 0, if I plug in 0 into here, I get a1 equals negative a naught over 2. Okay, so that's my first constant. So for when n equals 1, I get a2 equals negative a1 over 4. But I know a1 is negative a naught over 2. So I get negative a naught over 2 over 4. Just be careful with your negatives. So I just get a naught over 8. So a2 is just a naught over 8. Okay, let's just do one more. Let's just go up to n equals 2. We don't need to get a bunch of these. So if I plug in n equals 2, I get a3, and I get negative a2 over 6. All right, and so that means I know what a2 is. I'm going to plug that into here. That means I get negative a naught over 8 all over 6. So I get negative a naught over 48. So that means a3 is negative a naught over 48. Yeah, let's just stop there. I think the next a4 term will just be a very big denominator. I think we're good with just a3. All right, great. So that's for our first solution. Now let's use our second solution. So for r equals 0, our recurrence relation is an plus 1 equals negative an over 2n plus 1. Okay, great. So let's find some terms. Let's also go up to a3. So we'll stop there. So for n equals 0, if I plug in n equals 0 into my recurrence relation, I get a1 equals negative a naught over 1, which means a1 just equals negative a naught. Okay, easier to work with. So that means n equals 1. I'm going to get a2. That'll be negative a1 over 3. Plug in a1. I get negative a naught over 3, which is positive a naught over 3. So that means a2 is a naught over 3. Let's do one more. Just like last time. N equals 2. I get a3. This would be negative a2 over 5. But I know what a2 is. So we'll plug that in. So I get negative a naught over 3 over 5, which is negative a naught over 15. So a3 is just negative a naught over 15. Okay, so we basically have found two power series solutions with their respective roots. So our solution here, right, is going to be y equals, x to the r times that specific power series. Okay, and that specific power series, if we expand that a bit, it's going to look like a naught plus a1x plus a2x squared plus dot dot dot, right? So we actually have two of these series, each for their respective r value, r equals 1/2 and r equals 0. So we have our two solutions. Y1 is going to equal that x to the 1/2 because that's r equals 1/2. That's our first solution. And it would be a naught plus a1x. And we found a1 to be negative a naught over 2. A2 was a naught over 8. A3 was negative a naught over 48. So we'll plug all those values in. So let me actually erase this. This should be minus a naught over 2x plus a naught over 8x squared minus a naught over 48x cubed. And we stop there. And my second solution is when r equals 0. So this would be x to the 0 times a naught minus my a1 was negative a naught. My a2 was a naught over 3. My a3 was negative a naught over 15. So let's plug those in. A naught over 3x squared minus a naught over 15x cubed plus dot dot dot. So those are my two solutions. So my two solutions, two, we could say power series solutions. All right, but if we write this as a general solution, so therefore the general solution, okay, so we could clean this up a bit. They all have like a naught in common. So what we can do is factor out a naught out of both of them and let that a naught equal C1 and C2. Well, I won't say that C1 and C2 equal to each other, but we'll say a naught equals C1 and C2 because they're going to be different constants, but we're going to let a naught equal that. So we're going to factor out a naught out of all of them. And what we would have is y for our general solution, C1, that would be our A naught that we factor out. C1 x to the 1/2 times 1 minus 1/2 x plus 1/8 x squared. Let me write these a little better. 1/8 x squared minus 1 over 48 x cubed plus dot 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 plus C2 times 1 minus x plus 1/3. Excuse me. Why is it just C2? Well, because x is 0 just goes to 1. So that just goes away. We don't really want to write like 1, but that's why it's just C2 times all this. But yeah, C2 times 1 minus x plus 1/3 x squared minus 1/15 x cubed dot dot dot. Okay, and those are our power series solutions and a solution to this differential equation. Okay, so just to kind of recap, very long problem. Thank you for staying with it. Little bit of a difference is that we use this initial equation to figure out what our roots are ahead of time. And then when we started doing the problem, we saw that we got those same roots, which means we're on the right track. We were doing the problem correctly. And yeah, just a lot of, algebra work and things like that with the power series, but it's sort of the same where you insert in the y prime, y double prime, and you need to combine some power series, factor some terms out, clean up some algebra, uh, factor out next to the r, peel off an index shift, and combine into one power series, and then set up your recurrence relation, get your initial roots, and then solve for your power series for each root. Okay. So very long. Thank you for staying with it. Um, appreciate following along, but that's it for this video. Thank you for watching, and I'll see you in the next one. Take care.